Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. To continue our discussion on the basic elements, let's take up the one-dimensional beam element. This is slightly different from the truss element which we talked about, and this I have taken up so that we can illustrate how difference matrix, some other type of element can be derived, as well as we will also have a look at rigid body motions and the number of equilibrium equations it has, how we can find out. So this will give you a little bit an insight again into the solvability of the matrix equation. So the beam and all these things have different sign conventions. So let us one-dimensional beam. Let us take So in this, we will just take a one-dimensional element, x-axis here, and then beam is obviously is going to have a transverse deflection, and it's being acted upon by the forces in the transverse direction, and then it will have the important other ingredient of the deformation is the slope. Okay. So this is the transverse deflection we are going to do here. The way we show it together with the slope is that this is going to undergo this is exaggerated, of course. So this is acted upon by F1 y F2 y together with M1 M2. So these are two nodes, 1 and 2 here. Two nodes here. And it has a vertical deflection, which we call it as the vertical deflection here is V1. And then it has a slope here. So slope is measured as like this one, theta 1. Theta 2. So here V1 and then this is V2. So V1 is the vertical deflection here, V2 is the vertical deflection at node 2, and together with the slope theta 1. So slope is measured from horizontal axis to the tangent of this beam. So beam has taken this shape. Okay. A vertical deflection as well as going through slope. So all these deformations are really exaggerated, but this is the configuration. So all these things are the positive configuration here, axis, horizontal axis, and y is the vertical axis, and z axis is into the board. So you can see that vertical deflection is taken to be positive, and then this theta1 here, the slope is about the z-axis, again a positive configuration. So everything is shown in a positive sense, both the forces and the deformations. So here each node has 2 degrees of freedom, and then there are 4 in generalized force components. So what we want to find out here is the relationship between one element the stiffness matrix here multiplied by the displacement. So V1, theta 1, V2, theta 2, and here F1 Y, M1. So these are the displacements and the forces. So this is the K here. So you can K1, K12, 1, 3, 1, 4, like this, K4, 4. Okay, so this is how we write down. So to find out this, we recall our strength of materials approach. So for that, what we would like to do here is that we will just take up strength of materials thing. So where we have a cantilever here, which is acted upon by this. So this is a simple formula. Okay, so this is how we get it from the cantilever being acted upon by a force here. So this is essentially we are trying to follow the earlier approach of unit displacements, in the sense that if you keep this V2 and theta to 0 and give some V1 theta 1, so what we get here are the components here, K11, K12, K21, K22, right? And of course, these things. So here we have our, so you call it at delta 1 or V1. PLQ by 3EI, and theta here is PL square by 2EI. I'll have a negative sign here, in the sense that in the actual reality, so the curve of the shape of the beam would have been like this, right? Like this, if you recall. But however, since we are showing it as theta 1 in the positive direction, so we are going to give a negative sign for this one, like this one. Okay. So similarly, we also apply a moment here, and similarly here again. So this is V1 prime and this is V2 prime. So again, these things which we have here are So this is from the strength of materials you were saying. So what we have here is that V1 theta 1 prime here. So these are due to P, and whereas here this V1 double prime theta 1 double prime because of the M. So we can combine it. So under the action of both, so we have so this is what we have under the combined action of P and M. So this is the deflection and this is the slope which you have here, right? So what actually which we need here is that we don't need V and theta in terms of P and M, but we need P and M, which is F1y and F1 in terms of V1 and theta 1. So so essentially what it is that, so you can do here in the sense that you can even write this one here as a matrix here. So this is what comes from the strength of materials, and so that means that essentially you have to invert this P and M. So if you want to write P and M as an inversion of this one, so we can write well EI y L cube plus 6 EI So now we wrote it as P and M. So that's nothing but, these are nothing but your F1y and M1. So these are applied at the node 1. So what happens to the other one? So the other V2 and theta 2 are 0. V2 and theta 2 are kept 0. And then these string are put 0. And then we try to find out what is necessary of F1y and M1y. What about F2y and M2? So F2y, for example, so what will be the value? Here you put it as P and M here. And what happens to the 2 here at node 2? If you think that this is F2y, so F2y obviously will be minus F1y, keeping the equilibrium in mind. And what about, so if you have M2 here, so M2 and with F2y and P, so you have to, in fact, the equilibrium of the moment or M1 plus M2, and then, and if you want to put it here, P, this is minus F1y into L. So this way we have these things also. These things means in the sense that the two other component of the first column, first row. So that way you can find out the complete K matrix. So let me give the complete K matrix here. Okay. So the complete K matrix So these two are from equilibrium. Okay, so finally F1y In fact, the interesting part which you also should realize is that once you calculate the first row here completely, so which means that you can also fill it up automatically the first column here. Okay, so like this, you should be able to calculate what are the other complete values here. So we did this also. So essentially, if you want to do this one, it's not as difficult as it seems to be. So these things, if you want to calculate, it's essentially you are applying the forces at node 2 and keeping the node 1 completely fixed here. Okay, so this is, we are following the same logic as giving a unit deformation, right? Okay, so this is as far as the stiffness matrix of a beam element is concerned. So why I took this one is that this together with the truss element will form a frame element. What is a frame element? Frame element is nothing but a generalized one-dimensional element which can take the not only the axial loads, but it also is able to take the lateral loads, including the moments, maybe sometimes even the torsion. So it can even be able to take the bending in other directions as well. So frame element is a very generalized element, out of which the truss element is the simplest, and there's the beam element, and then all these things can be combined and as well as they transform into other higher degree dimension. Okay, so what I was trying to talk about is that what is the rigid body degrees of freedom here for this element. So for that, so let's take a numerical example of anything for that matter. Let's just take L is equal to 2. So what we are trying to do is that taking L is equal to 2, so we are trying to understand what are the rigid body degrees of freedom, what in fact what are the equilibrium equations, number of equilibrium equations. So how to get it right from looking at the matrix. So taking L is equal to 2, so what it looks is the stiffness matrix. You can also put 2E by L cube, and you can take it to be for simplicity, you can take it to be 1. So just assume it for simplicity. So if that's the case, so then we'll drop this one, and we have 6 minus 6, 6 So in fact, we've taken this k by L is equal to 2, and then this I have not filled up as it, and I'll fill up what should be the value. In fact, we are going to find out what should be the values of these things so that it is a viable structure. We know that we cannot arbitrarily put the forces, and we should make sure that the forces are such that the equilibrium equations are satisfied. So let us look at this one. So what we have here is that interestingly, if you just do the augmented matrix here and so on, so what we do is that, so what kind of operation which we can do? Some simple operation which you can see here is that third row is more or less like the first row, except the sign is opposite. So, and then there's also another relationship here, something, a linear operation is there. Okay. In fact, you can even do Gaussian operation here, in the sense that you can take everything to be 1 here and then subtract from here by appropriately multiplying, so that this will be 0 and this will be. So similarly here you can add something of this one, a multiple of this, so that this becomes 0, and so it's a Gaussian elimination process. So if you do that Gaussian elimination process, so the bottom 2 rows can be eliminated, and so performing Gaussian elimination, so you can make this one and then remove all these things. So similarly here you can take this one and eliminate all others by appropriately multiplying and making that 0. So in this process, what happens here is that, so I'll just write it here. I'll tell you what is the operation I've done. And here we have taken F1. We have taken some value here, F1. So let us say we have taken, I will explain you that this is, so we have taken F1 to be 10, M1 is 15, F2 is equal to minus 10, and theta, sorry, this is not theta 2, M2 is 5. So I'll just explain why we have taken that. I'm just illustrating it with a numerical thing. So by what is that I've done here? So in fact, the third row you can very easily see, you can eliminate it by doing this one. So similarly here, so here the third row, the operation here, R3 prime here has been, is nothing but R3 plus R1. So similarly here, so the fourth one, R4 prime, is R2, sorry, R4 plus R1 plus L into R3. Okay, so these are the row operations. By doing this, L is 2, of course. So you can obtain this one, and the third and fourth rows have been made 0. So in this process, what we have here, there's also another thing here. One more is coming from this one, is minus. On the right side, you have this 2.5. So what we have here is that the third and fourth rows have been made 0 by doing this operation. So what is this operation here? So if this is going to be, since that row is going to be 0 on the left side, so on the right side also it has to be 0. And by doing this, so this is what is going to be 0 here. So what are these things here? So the things here is that this operation says that the vertical forces have to be added up to 0, whereas this operation shows that it is the moment of all the forces together with the applied moments also have to be 0. So these are the two equilibrium equations for a beam. So by doing this one, so we are able to eliminate the third and fourth rows. Okay. So in fact, these you can see, in fact, that's how what we have applied here. In fact, this force which we are applying here is opposite to this one. And in fact, together with these moments and the forces, so we are able to get the moment equilibrium also. So that way, so we have two equilibrium equations satisfied, and so that means that we have two rigid body modes. So quickly, if you do this using this here, so we can so those two equations can be solved like this, and the total solution here will look like this one. So taking these two onto the right side, so this is what we get. So if you look at this one, this is the complete solution of the four components, and this is the one which we call it as a particular solution by the application of these forces, and then these two are rigid body displacement modes, in the sense that you can, if you apply this one with the stiffness matrix, you will get a 0, 0, 0, 0, 0. So similarly, this also will get a 0, 0 force component. So that means that to get these displacements, so we need not apply any forces, or so that means that the beam will not undergo any elastic deformation. So it's a rigid body mode. And then this is the deformation, elastic deformation, which you have got by the application of the forces. So in fact, as I kept telling, so that these rigid body modes are not necessarily these things. In fact, any combination of this is also a rigid body deformation. So in fact, can you see that this is in fact 1010 is nothing but, so if you have a beam like this one, what is 10? So that means that there's a displacement here, and then there's an equal displacement here, and then there is no slope. So that means that the whole beam has moved in the vertical direction without any deformation. So that is why you can see very well that this is a rigid body deformation. On the other hand, what is this one? So this is nothing but the second rigid body motion is nothing but if this is, what is this? So that means that you have a -2 here, and then you have, so there is a vertical displacement of -2, and then this slope is equal to 1. So you can see that the slope continues to be 1 here and 1 here. And so this is also a rigid body deformation because the whole beam has rotated without any slope deformation. So these two, that way you can very easily see that these two rigid body deformations we can have without any elastic deformation in the beam. So these do not require any application of the forces. Okay. So whatever I have here, this is the particular solution. This is the called the homogeneous solution, or we call it as the vectors in the null space. So that way, I hope together with the truss element, now with this beam element, I hope the number of equilibrium equations, so these are the equilibrium equations, and how they are related to the rigid body modes. So the number of equilibrium equations are equal to the number of rigid body modes. So that means that to get this solution, so these two have to be fixed arbitrarily depending upon your displacement boundary conditions. So automatically, or on the other hand, you apply the displacement boundary conditions so that the rigid body modes are eliminated, and then you get a solution. You get a solution for this one. So I think I'll complete it here, and then in the next class we will start the finite element application to continuum bodies. Okay, thank you.